so we're talking about conditional probability, right? We're continuing to do conditional probability. And so today we're going to talk about a couple of the most interesting, famous problems related to conditional probability. First one, a lot of you have seen in some form or other, and that's called the Monty Hall problem, the three-door problem. Very, very famous problem. It was, it's been in movies and TV and, New York Times articles about this. There are entire books written just about this problem, popular books on just this entire problem. Okay, so a lot of you have seen it before, but I'm not assuming you've seen it. Even if you have seen it, though, then I'm hoping I can give you some additional ways to think about it, and we'll approach it from more than one perspective, because it's a very subtle problem. And this is the sort of problem that almost everyone gets wrong the first time they see it, and then if they think about it for a while, they think they understand it, and then you ask the same question just in a slight disguise, and then everyone gets it wrong again. So I'm going to try to talk a lot about how do you really think about this so that you won't get fooled if I ask the same thing and then just change a few things around, what's really going on here. But anyway, I'm not assuming you've seen the problem before, so let's start from the beginning. So Monty Hall is a game show host. He's retired now, but for many years he hosted a game show on TV called Let's Make a Deal, and so the problem is named after him because it's not exactly what he did on his game show, but he did kind of similar types of games on his show. So the game is like this. There are 3 doors. Let's just call them door 1, 2, and 3. And suppose that you're the contestant on the game show. Monty Hall asks you to choose, and right now you don't know what's behind each door. Monty Hall asks you to choose a door. Okay, so say you pick that one. So there are a lot of assumptions in this problem. We're supposed to assume that one door has a car behind it. The other 2 doors have goats. So you don't know which one. One of these has a car behind it. The other 2 have goats. And so we're assuming that you, the contestant, have no idea which one has the car. They're all equally likely. But we assume that Monty Hall knows which is which. So Monty knows which one has the car. Okay, that's a key assumption of this problem. Sometimes it's kind of left implicit, and I think it's important to state that explicitly. It's a different problem if Monty Hall doesn't know. Okay, so one door has a car, two doors have goats. You pick one. Another assumption is that you want the car. You do not want the goats. Okay, so you pick a door. Suppose you pick this one. So let's say you pick this one. Pick this one. Just by symmetry, we can simplify things if we assume that we being the contestants, we choose door 1. If you want door 3 instead, that's fine with me. We could just renumber the doors. Okay, so let's assume that we pick this one initially, door 1, just to simplify the notation. Then what happens is that Monty opens up either door 2 or door 3, revealing a goat. Okay, so for example, he opens door 2 and there's a goat there. Okay, so then the car is either the one you initially chose or door 3. The question is, should you switch? Monty Hall gives you the option of, do you want to switch to the other door that's unopened or keep your original choice? The question is it beneficial to switch? Okay, so that's the problem. And there's one more assumption which is that Monty always opens, he's always going to offer you that choice. So he's always going to open a goat door. I'm just saying goat door is a door with a goat. Okay, that's an assumption. But if Monty opened a door that had the car, then it's a stupid game, right? Okay, so he's always going to open a door with the goat. That's why he needs to know. Otherwise, by chance, he might spoil the game. There's one more assumption that usually doesn't get stated, but it's actually pretty important. If he has a choice of which door to open, he picks with equal probabilities. And the case where that happens is if initially you guessed right, so the car is here, these ones both have goats, so Monty could open either door 2 or door 3, assume those are equally likely. On the strategic problems, I posted the new homework, the new strategic practice. On the strategic practice, you'll find a problem there, which is kind of an extension to the case where what you might call like lazy Monty Hall, where he's like standing here and he prefers opening door 2 to door 3 because he doesn't want to walk all the way from here to here. So suppose he opens this one with probability p, this one with probability 1 minus p, where maybe p is greater than 1/2 or less than 1/2 or whatever, if he has a choice. Sometimes he has no choice, right? Because he's not going to spoil the game. But sometimes he has a choice. But for the basic problem, we assume he picks with equal probabilities. Okay. And the question is, should you switch? And most people, when they first hear this problem, they say, okay, well, suppose you open door 2, and you're picking between door 1 and door 3. There's 2 doors. You don't seemingly have any information about whether door 1 or door 3 is more likely. It looks kind of symmetrical, so it's 50-50. And controversy has raged about this problem for years and years and years. Part of the controversy is because people don't understand probability and they haven't taken Stat 110. Part of the reason for the controversy is that sometimes some of these key assumptions are left implicit, and so then different people might interpret it differently. So it's important to have these assumptions clear. Under these assumptions, the answer is that you should switch. And if you switch, your probability of success is 2/3. And if you stick with your original choice, your probability of success is 1/3, so it's better to switch. It's not 50-50. We can't, it's sort of like an abuse of the naive definition of probability, I'd say, if you just immediately say, well, it's 50-50 because there's 2 doors and we don't know which is which, well, that's the naive definition, right? Assuming they're equally likely, but why are they equally likely? We don't know. We don't know that they're equally likely, given the evidence. We are assuming that initially, I didn't write this, but I said it. Initially, it's 1/3, 1/3, 1/3 as the probabilities, okay? But that doesn't mean that conditionally, after we observe what happens, it doesn't mean that it's still equally likely, okay? Because we have information. We have the information. One key intuitive point. Suppose that Monty opens door 2, just for concreteness. Well, obviously we know that door 2 has a goat. But so the kind of naive approach would be, well, let's just condition on the fact that door 2 has a goat. And originally it was 1/3, 1/3, 1/3, and we're getting rid of this, so then it's still 1/2, 1/2 for these. There's a subtle flaw in that reasoning. So we know door 2 has a goat, but a key thing with conditioning is we want to condition on all the evidence, okay? The evidence is not just that door 2 has a goat. We need to condition on all the evidence. There's one more key piece of information there. That's the fact that Monty Hall opened door 2. So now we're going to start thinking about why does that matter that he opened that door. So it's not just that we're not just conditioning on there being a goat there. We're conditioning on the fact that Monty Hall opened door 2. So we have to kind of see, why is that relevant? Why does it become 2/3? Okay. Door 2. All right. So I want to approach this problem in a couple different ways. Maybe 3 different ways. One intuitive, one with a tree, and one with a probability calculation. Okay, actually 2 intuitive ways. There are a lot of ways to think about this problem, but some of them are wrong. So I'm going to show you some correct ways to think about this. So first of all, a tree diagram, I think, is a very good way to picture this problem. So let's draw a tree. So you choose the door. I'm just to simplify, not having to draw as many branches, I'm going to assume that we choose door 1. the contestant chooses door 1. So choose door 1. Door 1. Okay, now it branches depending on which door Monty Hall opens, right? Monty Hall, there's two things. One is what's the door that has the car, and the other branching is what door does Monty Hall open, okay? So let's actually do the door that has the car first. So it branches 3 ways, and these branches each have probability 1/3, 1/3, 1/3, door 1, door 2, door 3. So this is just a car door. By car door, I don't mean the door of the car, but the door that has a car behind it. That's either door 1, 2, or 3, right? And they're equally likely by assumption. So that's the first branch. Secondly, we have Monty door. That's whatever door that Monty Hall opens. And let's just consider the cases. We choose door 1. The car is behind door 1. Then Monty Hall can open either door 2 or door 3. So that's where he has 2 choices. And so it branches 2 ways. Then he opens door 2 or door 3. And we're assuming those are equally likely. So I'm putting 1/2, 1/2 on those branches. Now, if we pick door 1 and the car is behind door 2, then Monty Hall has no choice but to open door 3, right? And then he'll offer you, do you want to switch to door 2 or not? So in this case, he has no choice. So this has probability 1. And then lastly, we pick door 1, car is behind door 3, Monty Hall has no choice but to open door 2 to reveal a goat, right? So that has probability 1, door 2. Okay, so now, how do we actually use this tree diagram to get the answer? Well, we just have to consider cases. So suppose that Monty Hall opens, just for example, suppose he opens door 2. Okay, that means I'm going to show you how do you do conditional probability in terms of a tree. Okay, so what does it mean? Suppose we condition on the fact that Monty opened door 2. That means that it must be that we took this path here. I'll circle that one, or we took this path here, right? These two are now irrelevant. Just like when I was drawing the pebble diagram, when you condition on something, you delete from your space everything that you can now rule out, right? You rule out everything that's inconsistent with what you observed, and whatever's left would be these 2 cases. And now let's just see what happens. The probability of this path from here to here, I'm just multiplying because I'm assuming independent. Well, I'm assuming that 1/2 is the probability of going from here to here if you're at here. So 1/3 times 1/2 is 1/6. And for this branch, 1/3 times 1 is 1/3. And remember what I said, when we were doing conditional probability using the pebble world perspective, we deleted all the pebbles that are irrelevant, and then we renormalized, right, to make the total mass equal to 1. So if we want to renormalize 1/6 and 1/3, what we should do is just multiply by 2, because then I'm making it 2/3, 1/3. Now I've renormalized so that they add up to 1. And so what that says is that conditional on Monty Hall opening door 2, there's a 2/3 chance now that the car is behind door 3. And there's a 1/3 chance that it's behind door 1. So therefore, if we switch, we have a 2/3 chance of success. So what this thing, just the circling, just showed was that the probability of success, if switching, given that Monty opens door 2, because I was assuming he opened door 2, and we just showed, just by this tree diagram, that this is equal to 2/3. Of course, you could do the same thing if he opens door 3, just circle the other 2, same thing again, and it's still 2/3. Okay? So that's one way to think of it, just looking at what are the different possibilities. And let me just say, what does this say intuitively? What this says intuitively is 1/3 of the time, your initial guess is correct, and then you would fail if you switched, right? No matter what happened, you would fail because you got it right. But that's only 1/3 of the time. The other 2/3 of the time, your initial guess is wrong. Monty opens up a goat door, and then you should switch. So 2/3 of the time you should switch. You should always switch, because 2/3 of the time you'll get it right, and the other 1/3. The 1/3 where you're getting it right is where you were initially correct, but that's only 1/3 of the time. Okay? So that's the tree diagram, which I think is useful, but it's also useful to just see how can we do this as a conditional probability argument. You can do this problem using Bayes' rule, but actually I would prefer to just use the law of total probability here. So let's do this using the law of total probability, LOTP. When we're using the law of total probability, the key step is deciding what to condition on, okay? And one of the really nice things about statistics and probability that's basically unique to this subject is, with most mathematical subjects, if you have a problem, you can't just, and you're stuck, right? You can't just say, well, I wish that I knew this and I wish that I knew that. Well, you can say that, but it doesn't help you, right? In probability, you think like, I wish I knew this, I wish I knew that. That's giving you a hint as to what you should condition on. Then you just condition on it and you act as if you did know that, okay? So I mean, if I didn't name the law of total probability, but if I had, I would have just called it wishful thinking, right? It's like, what do we wish that we knew? Well, I don't know about you, but for me, the first thing I think of, if someone asks me, what do I wish that I knew? I wish I knew where the car was, right? So it's a pretty obvious thing to think about. That's what we wish we knew. So we wish we know car door. So that's what we wish. We wish we knew where the car is. So we're going to condition on that. That's all, okay? So we need to define some events. I'll just say let S be the event that we succeed assuming that we're using the switching strategy. So I'm going to assume that we're going to switch, and I'm going to see what's the probability that we succeed by that strategy. So assuming our strategy is always switch. Monty Hall is going to give us the choice to switch, and we'll say yes. That's our strategy, and we want to see what's the probability of success of that strategy. Okay, and then let's say DJ be the event that door J has the car. So I'm using D for door J has car, where J is just 1, 2, or 3. Okay, so that's just some simple notation. Now let's do a calculation of the probability of success. Law of total probabilities just says, well, condition on which door has the car. That's what we wish we knew. So to do that, that's just P of S given D1 times P of D1, which is 1/3, plus P of S given D2 times P of D2, which is 1/3, plus P of S given D3 times 1/3. So it's P of S given D1 times P of D1, right? But these are, P of D1 is the prior probability that door 1 has the car, and we're assuming that they're all equally likely to start with, so it's just 1/3, 1/3, 1/3 for these weights. Okay, now what's this? D1, I'm just assuming that, remember, we're assuming that we picked door 1, so that means we got it right initially, but we switched, so that's bad. This is a bad case, so this is going to be 0. It's never going to work in that case. Now in this case, we picked door 1, the car is behind door 2, Monty Hall will open door 3, and we should switch, right? So we have probability of success 1 here, 1 times 1/3. Similarly, in this case, it's going to work. So that's also 1 equals 2/3. So it's actually a very easy calculation, right? Because these probabilities are very, very easy to compute once we know where the car is. So it's 2/3. There's one slightly subtle point here, which is that this is the unconditional probability that our strategy will be successful. And you could say, well, what if we wanted the conditional probability given that Monty Hall opened door 2? Is that going to be different? But in this case, I defined it symmetrically. So by symmetry, we also have, we can make up notation for which door Monty Hall opens. P of S given, let's say, Monty opens door 2. That's also 2/3. You could write out another law of total probability calculation if you want, but all it's a condition on whether Monty Hall opens door 2 or door 3, but by symmetry, it couldn't be, because door 2 and door 3 are completely symmetrical until Monty opens one of them. So that means both the conditional and the unconditional probability of success are 2/3. Now, in the extension on the strategic practice that I mentioned, the unconditional probability is still 2/3, but the conditional probability changes because in that problem I said that Monty Hall is too lazy to walk over and open door 3 unless he has to, or that kind of thing. Then there's an asymmetry. But in this version, it's symmetrical, so conditional and unconditional works the same way. So, okay, so we get 2/3. And they're nice. You can easily find applets online. I put a link on the webpage for a nice one that the New York Times has if you wanted to try it out. There's one thing that, so just to tell you a little bit about the controversy over this problem, that controversy started raging when Marilyn Vos-Savant, who writes a column in Parade magazine, someone wrote in and asked this question. It was not 100% explicitly specified all the assumptions, but it was fairly clear that this was what was intended, and she basically gave the correct answer. And then thousands of people started writing in telling her that she was wrong, telling her that she was stupid, including people with PhDs in math, and just writing all these scathing, nasty letters to her, and that controversy was raging for a long time. And one thing that I find ridiculous about that is, well, okay, so most people's intuition about this problem are wrong, but if you think about it carefully, you'll get the right answer if you have some familiarity with conditional probability. But even for people who had no understanding of like any of the stuff I was doing here, this is a problem that, and this is true in statistics in general, you could just simulate it, right? It's very, very easy to try it out with a friend, 3 doors. You can just do it with cups and props and whatever. You can also do it on a computer very, very easily. Write a little simulation, try it out 1,000 times just via computer simulation, and you'll see that if you switch, you'll win 2/3 of the time. So I don't understand how people will still continue to argue with that when you just try it out, simulate it. You'll see 2/3 of the time you succeed by switching. I mean, it's just kind of mind-boggling. But maybe some of the math PhDs didn't want to actually, try it out because they thought that they proved that it was 1/2 or something. Anyway, so that's the Monty Hall problem. I wanted to mention one other intuition for this that's kind of unusual. Usually when we have a complicated problem, the suggestion would be look at a simpler case, right? But I did emphasize the fact that it's useful to consider simple and extreme cases, right? So an extreme case here would be, what if instead of 3 doors, what if we considered the Monty Hall problem with 1,000,000 doors? So you pick one of those 1,000,000 doors, and then Monty Hall proceeds to open 999,998 doors, leaving just 1 door should you switch. In that case, I've never met anyone who would not switch, right? I've never met anyone like that. Because with 1,000,000 doors, you're extremely confident that your initial guess is wrong, and you're extremely confident that that one remaining door has the car. Conceptually, though, there's no difference between that and this. It's like, 3 doors or 1,000,000 doors. It's the argument for 1/2 here would apply in the same way with 1,000,000 doors. It's just in that case, everyone sees intuitively that it's ridiculous, and here, people don't have that intuition. So anyway, that's another intuition for the problem. All right, so that's the Monty Hall problem. You should look at the strategic practice problem, and on the homework, homework 3, there's an extension with more than three doors that you can think about. I'm talking on that problem about the case where Monty Hall possibly leaves more than one door still unopened. But anyway, you can work on that later, but this is just an introduction to the Monty Hall. So it's a very famous, fun problem, but I think it also illustrates a lot about how to think conditionally, right? Like the tree is useful. This perspective is it's just the problem is really easy when you set it up this way, but if you just try to apply naive intuition, then most people get this completely wrong. Okay, so let's do another example. So this example is called Simpsons Paradox. It's another kind of notorious problem or paradox that comes up. It comes up a lot in everyday life, and it's another problem where most people see it the first time, it seems impossible, and then they think they understand it, then change a few things around, and then they fall for it again. So it's I love paradoxes in general, so we'll be seeing a lot of paradoxes in this course. So the best way, I mean, I could start, making up some abstract notation and stuff, but the best way to start understanding Simpsons Paradox is to see some examples. So I'll write down an example, and then we can discuss that, and then we can try to write out what's the more general thing that's going on. By the way, there is no such thing as a true paradox, a real paradox. If there were a real paradox, we'd have a contradiction, and the universe would explode, and we would not be here. So there are no paradoxes in the literal sense. What it is, though, is something that's deeply counterintuitive to most people, which means it forces you to think harder. And if you think hard enough, then eventually you understand that actually it does make sense, but you have to think hard, okay? So here's the problem. One example. Is it possible to have two doctors where the first doctor has a higher success rate at every single possible type of surgery imaginable than the second one? So name any surgery, first doctor is more successful than the second doctor, measured in terms of percentage of successful outcomes. Yet, the second doctor overall has a higher success rate. That's the basic question. Okay? Well, Simpsons Paradox says that that's possible. And at first that sounds wrong to most people because it sounds like if person A is better than person B in every single category, then when you aggregate those categories together, it's not going to somehow flip, right? Except that's wrong. Simpsons Paradox says it can flip, that the sign of inequalities can flip when you aggregate data together. So one thing seems better than another in every individual case. You add up all those cases to get the total, and then it flips which way it is. Okay, so that sounds really weird at first. But I'm just going to illustrate it through a very simple example, and if you think carefully about this simple example, then you can see what's really going on there. Why is that possible? Okay, so I like to illustrate Simpsons Paradox through examples that I make up based on The Simpsons, as I've been watching The Simpsons since I was a kid, and I like the show, and it helps me remember the example that it's Simpsons Paradox. So I don't know how many of you watch The Simpsons, but it doesn't matter if you do. On The Simpsons, there are two doctors, Dr. Hibbert and Dr. Nick. Okay, so now the data that I'm going to give you are made up. They don't actually tell you the percentage of success on the show. Okay, but anyway, Dr. Hibbert is kind of the reasonably well-respected town doctor that everyone who can afford to goes to, but he's going to charge a lot. Dr. Nick is the guy with like the infomercials on TV who advertises that he'll perform any surgery for $129.99. Okay, so probably most people would consider Dr. Hibbert to be the better doctor, and Dr. Nick is kind of like a cheap quack doctor. Okay, now I made up some numbers. So suppose, for simplicity, to understand the paradox, we only need to consider two types of surgeries. Once you understand what happens with two surgeries, you can easily see what would happen if you had, like, 50 different types of surgery. But to understand the crucial phenomenon, we may as well just assume there's 2 doctors, 2 different types of surgeries. Okay? So I made up some numbers, and we can summarize everything in terms of 2 2x2 tables. Okay? One table for Dr. Hibbert, and one table for Dr. Nick. And I'm going to fill in some numbers. So these tables represent 2 types of surgeries and success or failure. So let's just write success here. First row is for success, second row is for failure. So each doctor performs a certain number of surgeries. And to simplify things, I think I assumed that each doctor performs 100 surgeries total. So there's nothing going on where you can say one doctor is doing a lot more surgeries total. This is success, failure for Dr. Nick. And let's assume that there are only 2 types of surgeries. One is heart surgery. And the other one is, I just made up an example, Band-Aid removal. I've just tried to make up something that seems hard. I'm not a doctor, obviously, but, well, doctor of philosophy, but it doesn't count. One is an easy surgery and one's a hard, difficult surgery, okay? Like Band-Aid removal, I can do. Now, I can't do heart surgery. So, all right, so I made up some numbers. So suppose that Dr. Hibbert performed 90 heart surgeries and succeeded 70 times, failed 20 times. And suppose that he performed 10 Band-Aid removals and succeeded all 10 times. Now, Dr. Nick performed 10 heart surgeries, succeeded twice, failed 8 times. That's kind of sad. He performed 90 Band-Aid removals. He succeeded 81 times, and he failed 9 times. Somehow he failed 9 times at the Band-Aid removal. Now, how many of you would rather go to Dr. Hibbert than Dr. Nick? Would anyone here prefer to go to Dr. Nick based on this data? Yeah. Now, it seems, okay, well, I would definitely prefer to go to Dr. Hibbert. But on the other hand, you could argue from this that Dr. Hibbert is successful 80% of the time, and Dr. Nick had 83 successes. So he can, on his infomercial, he can say he succeeded 83% of the time, and that 3% better than Dr. Hibbert. And you're paying so much less for a 3% higher success rate. So what did we do to get 80 and 83? We were just aggregating, right? Here I listed out separately by surgery. Here we aggregated. Notice that the direction flipped, okay? So for each individual surgery, Dr. Hibbert is better. So that's conditional, right? So it's the difference between conditional and unconditional. Conditional on which type of surgery? If you condition on performing heart surgery, you'd rather have Dr. Hibbert. If you condition on having Band-Aid removal, you'd rather have Dr. Hibbert, right? But unconditionally, Dr. Nick has a higher percentage rate, and the reason, you can see it here, I just made this up as a kind of an extreme example so that you get some intuition. You see what's going on is that 90% of Dr. Nick's surgeries are Band-Aid removals. Well, Band-Aid removal is so much easier than heart surgery that it would be very easy for him to get a higher success rate because he's doing easier surgeries. And you can see, I mean, of course, this is just made up, but in, in real examples, you could imagine that, maybe like the most famous and most renowned, best like neurosurgeons in the world could be that their success rate isn't as great because they're getting the hardest cases, right? They're getting the cases that no one else knows how to deal with, so you refer it to the world's leading expert, and then that's going to hurt their success rate, right? So that's what's going on. That's an example of Simpsons Paradox. I think when you see this example, well, it's clear how that can happen, and yet when, in problems that are completely the same, just in a different language, different setting, then it sounds like it's impossible. How can it flip like that? Okay, so Let me explain it a couple other ways and mention a couple other examples. Another way to think of Simpson's paradox, well, here's another example. In baseball, it's possible to have two players where the first player has a higher batting average. A batting average is just what percentage of times they were at bat that they got a hit. One player has a higher batting average for the first half of the season and for the second half of the season, yet if you look at the whole season, the second player has a higher batting average. And again, that sounds impossible at first. If you're better for the first half of the season and better for the second half of the season, how could you be worse for the whole season? But you can see it's basically the same problem, is that you can easily make up some numbers to illustrate that. So it can flip. What's really going on here, another way to look at it, is just in terms of adding fractions. Okay? So if you had like 1/3 plus 2/5, well, let's see, I haven't added any fractions in a while, but I think you're not supposed to just add the numerators and add the denominators, right? This is not equal to 3/8, right? That's our inequality for the day. That would be if you haven't studied adding fractions before, when you're learning for the first time, that's kind of the obvious thing to do. Add the numerators, add the denominator. Well, that doesn't actually work, right? However, if you added fractions this way, that is closer to how you aggregate, right? Because we're just adding up successes and adding up trials, right? So that is sort of how we do the aggregation here, right? Add up the successes, add up the total number of trials, that kind of thing. So if fractions were added this way, then Simpson's paradox would not occur. But since that's not how we add fractions, it doesn't happen. Okay, and there are a lot of other examples of Simpson's paradox. If you just look at the Wikipedia entry, and you can find as many as you want, examples that happen in real life and actually have policy implications and legal. There are some interesting legal cases involving Simpson's paradox. Let me talk about how do we express Simpson's paradox in terms of conditional probability. So just to kind of map this example into some events, let's let A be the event that surgery, suppose someone's going to have surgery, and let A be the event that the surgery is successful. And then we'll try to write out, in probability notation, what is this example saying, okay? So let A be the event that the surgery is successful. Let B be the event that we're treated by Dr. Nick. And then there's one more event that so B complement would correspond to Dr. Hibbert, so we don't need separate notation for that. And then we need one more event, which is what type of surgery. So let's call that C. C be the event that we have heart surgery. So C complement is Band-Aid removal. Okay? So those are the events that we need. And let's just write out in probability notation what are these tables telling us. Okay? Well, what's it saying? It says the probability of success, given that we're treated by Dr. Nick and we're having heart surgery, is less than the probability that the surgery is successful, given that we have Dr. Hibbert for heart surgery, right? That's just comparing the two heart surgeries. Now, what about for Band-Aid removal? The probability of success for Band-Aid removal, again, it's less likely to have success with Dr. Nick than Dr. Hibbert. So this is just going to be A given B complement, C complement. Okay, so those are the two statements we have. But overall, when you aggregate, aggregating means don't condition on the type of surgery. Then we're just looking at the overall. So overall, the probability of A given B, that is success given that you're being treated by Dr. Nick, is greater than the probability of success given that you're treated by Dr. Hibbert. So notice it looks like these expressions look similar, And it looks like if you combine these two cases, here, well, all of these are given B, A given B on the left, and we have the two cases, given C complement. Looks like if you combine those cases, you'd get this. But if you add up or combine these inequalities somehow, then you would guess that it would remain less than, but the inequality flipped. So Simpson's paradox says that this is possible. This is an explicit example showing that that's possible. C is called a confounder. So I chose the letter C because it could stand for confounder or control. It's something you want to control for. In this problem, it seems a lot more relevant to condition on what type of surgery you have, right? So the more relevant comparison would be the more conditional one in this case. And everyone here agrees that Dr. Hibbert is better. That means we should condition on more things. If we fail to condition on C, though, we can get a very misleading answer here, right? Because of the fact that if we don't condition on the type of heart surgery, what happens is knowing that we got treated by Dr. Nick gives us information about what type of surgery we had, which then in turn affects the probability of success. So that's Simpson's paradox, and this is just kind of like the general setting of Simpson's paradox. So basically any example of Simpson's paradox can be written in this form. So I would take the definition of Simpson's paradox is whenever you have these inequalities, but it flips when you aggregate in this way. That's a concrete example. That's just the generic setting. Okay, so you should try to think intuitively about why is this possible by thinking about examples. And think about why this is possible, and think about should you be conditioning on C. And then there's one other thing that I wanted to mention about this is why, just to go into a little bit more of the math of those equations, why is that actually possible? In the sense that the first time that I saw this, I thought that from here and here, I thought I could probably prove this because it looks like it's going to be the law of total probability. So I want to show you what goes wrong if you would obviously it's not going to work to prove less than here because we just saw an example that it could go this way. But what if you were trying to prove that this and this implies this with a less than? What would go wrong? I just want to show you quickly what would be wrong with that argument. So the basic argument would be, the obvious argument to make is I want to relate A given B to A given B and C. That means we need to use the law of total probability. So by the law of total probability, I would be conditioning on C. This is just the conditional form of the law of total probability. Conditional probabilities are probabilities, so I can do Bayes' rule, law of total probability, anything I want. It's going to work the same way, just everything is given B. So I'm conditioning on C, whether C happened or not, but everything is still given B. This is the conditional form, plus A given B, C complement, P of C complement given B. Okay? So this is, if you deleted the given B everywhere, this would just be exactly the law of total probability, right? And so therefore this is true because conditional probabilities are probabilities. So it's still true with given B's. Now, if we compare this with what we had, we know that A given BC, this thing is less than P of A given B complement in C. And this thing is less than P of A given B complement and C complement. Okay, so you would then want to plug those in. But at that point in the calculation, you're not going to be able to reduce it down to this. It's because of this term and this term, and we might call those weights. Those are conditional on B, right? And if we tried to write the same thing for P of A given B complement, then we'd have B complement here and B complement there. But we don't have any way to relate those weights for one case or the other. So it's not going to follow. So it's important to contrast this with the law of total probability, basically. Intuitively what this term is in that Dr. Nick case, this is the probability of performing heart surgery for Dr. Nick, which is very different from the probability of heart surgery for Dr. Hibbert. So the weights change, and that's what enables Simpsons paradox to happen. Okay, so let me mention one or two more examples of Simpsons paradox. So here's another one that's a pretty famous one that involved a court case. So what happened was that there was a lawsuit against UC Berkeley claiming sex discrimination in admissions to their graduate programs. That is, claiming that they were discriminating against UC Berkeley was discriminating against women for admissions to graduate programs. And something interesting happened in the sense that when you kind of looked at the overall admissions rates, it looked like UC Berkeley was making it easier for men to get in than women for grad school. So then seems like a clear-cut case of discrimination. When you look at the data more closely than that, then something different turned up, which was the fact that if you looked at each individual department, because when you're applying to grad school, you apply to a specific department, right? For each individual department, there was not clear evidence, right? So each individual department I'm not saying they were all exactly fair, right? But each individual department generally did not seem to be discriminating. But when you aggregated all the departments together, then it seemed like it was very unfair to women. And the reason is that certain departments are more popular for women to apply to relative to men, and certain departments are harder to get into than others, and somehow those things led to a Simpsons paradox occurring. All right, one more example of Simpsons paradox. This is actually the first one. I've loved paradoxes for a long time, and this was the first one I ever saw, and I still find it helpful to think about it. So we have two, let's see, how does it work? We have two jars like that with jelly beans, although if I were phrasing it now, I would use gummy bears. But I first learned this problem with jelly beans. There's two types of jelly beans, let's say open circles and closed circles, and two flavors of jelly beans, okay, in these two jars. And then there's two more jars here, okay? And there's more jelly beans. I'm not going to make up numbers or anything. All I'm saying is there are two types of jelly beans in each of these four jars. Now, okay, suppose that you like one flavor better than another. And so you get to choose a random jelly bean from this jar or this jar, right? But you just have to reach in, and you can't actually pick which color you're getting. So you just pick a random jelly bean from this jar or this jar, and suppose this jar is better than this jar. I put by greater than, I mean that this jar has a higher percentage of the one you like, right? And suppose this jar, you can make up your own numbers. It's actually good practice to make up your own specific numbers for this. Suppose that this jar is better than this jar, okay? That is, it has a higher percentage of the jelly bean you like. Now, suppose that someone then created a bigger jar, and then created a bigger, I should have used a board where I could write this below. These two jars, I just dumped everything into one big jar. So this one and this one all got dumped into here. And this one all got dumped into here, okay? So I combined the two better jars, and I combined the two worse jars. Well, naively, you'd think, well, I combined the two better ones, that's going to be better, okay? But then it could flip. And after you aggregate the jars, suddenly this one has a higher percentage of your favorite jelly beans. You should make up your own example, your own numbers showing why that can happen, and that'll give you a lot of intuition for Simpsons paradox. Okay, so that's all for today. Have a good weekend.